We're nearing the end of our videos here, and this one is going to be about functions written as power series. It's beginning to hopefully get pretty cool because all of the stuff that we've studied when it comes to series, convergence, divergence, etc., to me gets a little bit legal. You know, it's a matter of, does it converge, does it not diverge, under which conditions, etc. The stuff can get a little bit tedious, and you start to lose sight of where you're going. And in the next couple of videos, hopefully, we'll get you back on the track of figuring out, like, why would somebody care about this? Why is it cool? And it is actually really interesting and really strange. So we're going to start with a series that hopefully you are familiar with. So 1 plus x squared, etc. This thing is, of course, geometric. I should probably write that in here. So this is geometric, and hopefully you know a geometric series, or you understand what that is. For example, 1 plus a half, plus a fourth, plus an eighth, etc. This thing converges, of course. Its common ratio is less than 1, right? So this is a more generalized one, 1 plus x squared, etc. And the question is, first of all, let's write that in sigma notation. I should make a note that you should use the PDF that I posted associated with this file to help you through this talk. So this thing in sigma notation, first of all, not too difficult. Looks like that, right? And in the case when n equals 0, you get 1. If n equals 1, you get x, etc. And what is this infinite sum equal to? Well, we know that it is equal to, we know that it's geometric, so it's 1 over 1 minus the ratio. It's actually the first term over 1 minus the ratio, but in this case, that's 1. So 1 over 1 minus x. Which is a really strange thing when you think about it, that this thing, 1 over 1 minus x, is actually equal to this infinite series, right? That is, of course, given that the absolute value of x is less than 1. So, for example, the one I wrote up on the board a minute ago had 1/2 as the ratio. So 1 over 1 minus a half, that's 1 over a half, which is 2. And if you were to do 1 plus a half, plus a fourth, plus an eighth, plus a 16th, etc., the sum would converge to 2. Which, like I said, is a little bit weird that we've got this infinite series, and it's equal to 1 over 1 minus x. So this is a function that we can write as a power series, specifically this power series. Okay, using this fact here, let's express 1 over 1 plus x squared as a power series. So why don't you hit pause and attempt that for yourself. Okay, hopefully you have attempted that, and it's not very difficult. I know it might seem odd and you know, I guess extremely complicated looking, but all we're going to do is this x squared basically is holding the spot of that negative x. So we're basically just going to replace x with negative x squared. So I could write this instead as 1 over 1 minus negative x squared, right? And if that's the case, instead of being equal to the sum, of x to the n, it would just be equal to negative x squared to the n. Just remember your basic ideas of functions, right? If this is a function of x, and I've replaced x with negative x squared, then all I have to do is replace x with negative x squared. And now that series, when you write it out, will equal 1 minus x squared plus x to the fourth and then minus x to the sixth, etc. Which, by the way, again, is pretty cool, right? Like this function, 1 over 1 plus x squared, the function written in black here, 1 over 1 plus x squared, is equal to this infinite sum. And remember, we do have conditions on which we can actually make this substitution. Here we said that the absolute value of x has to be less than 1. So when you're writing a function as a power series, you definitely have to respect the fact that it doesn't always converge. And if it doesn't always converge, then you can't necessarily take any old function and express it as a power series. So all that legalese that we went through, there was a purpose to it, even though maybe it wasn't that elegant or beautiful seeming. So now another one, 1 over x plus 2. This one looks a little bit off from the form of 1 over 1 minus x. I'm actually just going to give myself a little bit of space here. It looks a little bit off from that, but give this one an attempt. So hit pause and then attempt it. Hopefully you've done that. So we can actually rewrite this in the following way. Two times 1 is still 2. 2 times x over 2 is x. And now, if you would now consider this as a half times that, now it looks a lot like, maybe even more to the point, we could say minus negative again. So now it's 1/2 times our sum. Right? And so this actually would be a power series representation of 1 over x plus 2. We should, or we can actually make this a little bit prettier by taking the negative 1 out, for example. And maybe even this 2. Folding the 2. I'm going to take that half and fold it in there. So there wasn't 1 over 2 out here. This was 2 to the n, so that's now 2 to the n plus 1. And maybe just so that you can see the difference between the coefficient and the variable component, there you can see it written as a power series. And now I know I've done a little bit of hand waving when it came to this radius of convergence. So let's look at this one in a little bit more detail. This thing converges when the absolute value of x over 2 is less than 1. Right? Going back to this thing. And that's true if and only if the absolute value of x is less than 2. Sorry that that looks like it's or equal to. It's not supposed to be. So we would say our radius of convergence would be like negative 2 to 2 exclusive. So this function can only be, function written in black, 1 over x plus 2, can only be expressed as this power series if x is between negative 2 and 2, excluding negative 2 and positive 2. So again, like I said, the legalese that we developed does have a purpose. Okay, I'm going to quickly do another one. I'm actually going to leave this geometric one up here. We'll be discussing it a little bit in a second. So x cubed over x plus 2. Give this one a try for yourself. It's variations on the same theme here. We're going to take the x cubed and the 1 over x plus 2. Right, x cubed times 1 over x plus 2. And then that's going to be x cubed times that thing, right? Because 1 over x plus 2 is the one we just studied. And then if you want to, you can also fold the x cubed term in there. So this is a power series to represent this function. And just because, let's write out a couple of terms here. It's pretty cool. I mean, again, we've got this infinite series that's actually the same thing as x cubed over x plus 2, again, whenever it converges. As I say in the PDF here, so far we've been kind of in this sort of obscure function land where everything is sort of a cousin of this beginning geometric series. And the reason I started with that, and the reason that a lot of textbooks will choose to start with that, is because that was really your first taste of a function written as a power series. You saw this thing 1 plus a half plus a fourth plus an eighth, and then maybe in Algebra 2 or something like that, you decided, oh, well, if you add that up, it does get closer and closer to 2. So we started from that, and we've had a few different things that sort of tangentially related to this thing. And now we're at this point, x cubed over x plus 2, which you might think of as some sort of familial cousin or something, or relation to this series. So we're going to endeavor soon to take on more complicated functions that aren't necessarily related to this. And that's what Taylor's series will help us do. So let me get rid of this now. Okay then. We're going to write 1 over 1 minus x squared as a power series. We know that 1 over 1 minus x is equal to that, which I just erased. Wise move. Think about how these two things relate to each other. And this is definitely a place for you to pause. And I would take like a serious 2-3 minutes, an actual 2 or 3 minutes, not like a pause and go to iChat or something like that. Pause, think about it. What does that function have to do with that function? Okay, so hopefully you have concluded, it would be great if you concluded that this one is actually the derivative of that one. Right? If that's the case, then this must equal 1 plus 2x. Remember, this was 1 plus x squared plus x cubed, etc. If this one's a derivative of that one, then we should get 1 plus derivative of 1 is derivative of x, 2x is derivative of 2, 3x squared plus on and on, which would be equal to nx to the n minus 1, where n goes from 0 to I'm sorry. That would be n equals 1, right? Because the first term is there. If we wanted, we could base this thing at 0. Wait. Sorry. And it'll be n plus 1, x to the n. So those are the same thing. I just changed the beginning index. But point being, we now took this power series that we knew and we related it to another function, not because it was a function of that function, but it was actually the derivative of that function. Whereas over here it was just a close relative, now we've got a derivative. We will next do the natural log of 1 minus x. Let me get rid of this. So again, think about what natural log of 1 minus x has to do with that stuff. The last two that we just studied there, or the last, I guess, the relationship between these two. The derivative of natural log of 1 minus x, I'm just going to write up here. The derivative of natural log of 1 minus x is actually negative 1 over 1 minus x. Digest that for a second. So take the derivative of that, and you'll get that. And this thing, well, we know that 1 over 1 minus x is that, so we're going to, let's leave, yeah, why not? So we're going to integrate this thing, right? So if we integrate this, we should get to the natural log. So first thing I'm going to do is ignore the negative. And this will effectively be like negative the integral of 1 plus x squared plus x. Right? And this is, of course, natural log of 1 minus x, because we set it up that way, right? And here we'll get x plus x squared over 2 plus x cubed over 3. And I took the constant from here and made it that. So we can now write this as a series, or in sigma notation, n equals 0 to infinity of x to the n plus 1 over n plus 1 plus c. And we should say again that we should respect the convergence. Yeah, so natural log of 1 minus x equals negative this sum. And I realized, yeah, so I changed the index here. And an IB note, checking my paper here so that I get all my notes for you. An IB note is that they actually will provide you and write it in this way. And if that's the case, then so IB actually, rather than giving you natural log of 1 minus x, they give you, like in their curriculum guide, would be 1 plus x, and then go from here. So that's one of the things that you're responsible for IB people. And they again, they write it in that way. It's not mandated that you write it in that way, but you should be able to recognize it in that form. I chose for 2 reasons to go with this form. One is that's the book that we have, and 2 is I think it relates directly to the initial geometric series that you've already studied. Okay. Lastly, we will look at arctangent, which is pretty cool actually. Note that the derivative of arctangent is this. We already did a power series for that. So arctan will equal the integral of 1 of this, which is the integral of that. Hopefully you can see the end of that, which will be constant plus x minus x cubed over 3 plus x to the 5th over 5. And in this case, we have a function here so that we can actually find c. Let's let x equal 0. And if x equals 0, then we obtain C is equal to arctan of 0, which is 0. So if C is 0, then you're left with that as your power series for arctan. And I'm going to rewrite that down here in black in sigma notation. Okay, so our accomplishments here have been taking basically this geometric series that you should remember from Algebra 2-ish, and then we went in various directions from it. We went to functions of this thing. We had a couple of offshoots there. Then we found something having to do with its derivative. It was this squared, right, in the denominator. And then we looked at this natural log function. And now we've also looked at arctangent because of another derivative relationship. The derivative of arctangent was some other function that we had already studied, which was closely related to our original power series with common ratio x. This is all building toward taking awesome functions, trig functions, things like that, and writing power series for them and discovering even more about their nature. So we will do that the next lesson.